Hello everyone, and today we'll be seeing one of the problem from Geeks for Geeks. It says, kth missing positive number in sorted array. So, given an sorted array of distinct positive numbers, integers ARR, you need to find kth positive number that is missing from the array. Now, if k is 5 and we are given array such like this, we have these many missing numbers 1, 5, 6, 8, 9, 10, and the fifth element from this is 9th, and hence the result answer is 9. Similarly goes with second example where array elements are 1, 2 and 3. No array element is missing, and hence the next subsequent elements, which are 4, 5, 6, are the missing ones. And here if k is 2, then the missing element is 5. So on so forth. Next, if we go ahead, 1, 2, 4, 6 are missing elements, and second element is 2. That is the question, and we have to solve this within expected time complexity of log n. How can we do this? First of all, one thing which directly comes into our mind is a brute force approach, which one can go ahead and say that, hey, I'll have 2 iterators and one for array and one for range. So as the range progresses and as the array elements meet, we would advance the pointers accordingly or iterators accordingly, and the moment and at those moments we will keep track of missing elements. And if missing elements is equal to k, then at that moment whatever element from the range we get, we will return that. So that is a brute force approach, but it will go ahead and it will use the length of an array, not to mention if the limit is too far, so it will go ahead and check the limit. So it will be O of max of k comma n in such a way. Can we optimize this? Yes, we can optimize this by using binary search. So how can we do a binary search over here? First thing first, we need to understand how this array is being stored. So let's take an example 2, 3, 4, 7, 11. I'll take an example 2, 3, 4, 7 and 11 with an indexes as 0, or I'll start with 1, 2, 3, 4 or 5. That would make our things simple. So these are indexes, but I have added plus 1 for simplicity. Now coming upon misses, how can we get this? So from till this point, how many element are we missing? We are missing one element, because till this point there can be one, but there isn't any one, and at 3 there's still one missing, so I'm taking 1. 4, 1 missing. At 7 there are 2 elements missing, 3 elements missing, that is 1, 2 and 3, which means 1, 5 and 6, because 2, 3, 4 are present, 5, 6 are missing, and hence we have the 7th element. That means 3 numbers are missing. So I'll write here 3 numbers are missing. And for 5, that means 11, we have nothing but 6 elements missing. How did I calculate this? A simple way to understand this is we have 11 minus 5. So if everything was within the picture, we can get the range something like 1, 2, 3, 4 and 1, 2, 3, 4 as array. So this being array, this being range. So I'll call this as range, which is from the index itself. So, or I'll just say instead of range I plus 1, and I'll just call it as array range or I plus 1. So yeah, we have got the understanding based on this. Misses, how many numbers are missing till that point, and we also have k. Remember, this misses would just keep on increasing, so these are in the monotonous increasing fashion. Now within a k, and we have a sorted list, you know better what can be the best solution. If k is 5, we can just go ahead and take this 5 to this position, right? So we have k which is equal to 3. Now tell me, at this point you have 3, you have to go to 5 because we need to have k as 5. How many steps you need to take forward? So there are plus 2 numbers I have to do. I have to make so that I can get the appropriate number. So that means I am having a number as 7. 7 plus 2 gave me 9. So that was the case over here, and 9 was a missing number. So is it 9 a missing number? That means our algorithm should tell us the apt position, and once we get the apt position, we should add k to it. So don't worry if things are not yet very clear to you. Things would be much more clearer when we get into our code. So right now we have the left l is equal to 0, r is equal to a dot length minus 1, and I'll use it a for simplicity, and while l is less than or equal to r. I'm having a binary search over here, so let's consider one element which I'll take as mid, l plus r minus l divided by 2. So we have a mid right now, and with this mid I'll count as missing count, or okay, I'll write a full name. Missing count is equal to a of mid minus mid plus 1. Why mid plus 1? Because you know it very well. Mid is an index, and index starts from 0, whereas we want to start our counting from 1. So 0 plus 1 is nothing but I plus 1, what we are doing, where I is the mid. Cool. Now let's check that, hey, if missing count is lesser than the provided k, and if it is lesser, we need to look further right. Look on right, because we wanted to get on the higher number. So left is equal to mid plus 1, else right is equal to mid minus 1. Similarly, but in the reverse fashion. Ultimately, the moment comes that this while loop would break, and once it breaks, we would have an appropriate position. Where would that appropriate position be? It would be on the right. So right plus k plus 1. Why right plus, or I would say right plus 1 plus k. So right, since being an index, we have to do a plus 1 here and plus k. So it's very similar to, let's take another example over here, 1 2 3, and we'll get to know this in a way that we have 1 2 3 with indexes 0 1 and 2, whereas our right and k is equal to 2. So missing numbers are 0 0 and 0, and since these are zeros, our target or our end right would be 2, and once we have right is 2, k is 2, we just wanted to sanitize this right as r plus 1, which is equal to 3, and 3 plus 2 is 5. In this fashion, we would get with our missing number, kth missing number. So R is chosen because R was the appropriate position at that point where we can fit the K. So in this case, it would have been this point. So far so good. Let's compile this code. For any compiler errors, there seems none. Let's try to submit this. Cool. It seems that it has passed the rest all the test cases, and this was a very classic program, or it was a very new kind of program with binary search. So if you wanted to know more about binary search or solve such kind of problems, click the video on your right, and I'll see you in the next one.